Yeah, so thank you for coming. So Aritra and Rigwick, they were featured in the TF Community Spotlight, and they're also working at PyImageSearch. They're kind of experts in machine learning, so I'm really excited to hear about this, and thanks for everybody for coming. I'll let you guys go. Go ahead.
Thanks for the generous introduction. We are no experts, but we try. So, so hey everyone, thank you for coming down to this talk. It's a talk on neural radiance fields, as it's a very hyped topic, as we all know from the recent Google I/O. We saw that Google Maps are featuring neural radiance fields. So what basically is neural radiance fields? We'll just wrap our heads around. So I am Aritra, and this is my this is my colleague Ritvik, and we both work at PyImageSearch towards making in-depth tutorials on deep learning as well as machine learning papers. So let's start. A few days back, when I was going through my photo gallery, I came across these three pictures. The first view of the staircase, the second view of a staircase, and a third view of a staircase. So these are all the same. These are all viewpoints of the same staircase, but different viewpoints. Why did I take three pictures, you may ask? I took three pictures because I wasn't sure whether I could capture this beautiful scene with just one photo. I was very worried that I'd miss the right perspective. So this got me thinking, what if there was a way to actually capture the entire 3D scenery just from these three pictures? So what I'm saying is not 2D images, but the entire 3D scenery from top, from down, from any perspective, just with some sparse images. That way you will be able to view exactly what I saw that day. In NeRF, that is neural radiance fields, Mildenhall et al. Proposed a method that turned out to be just what I needed. So this is just like an input and an output kind of a scenario with what we could achieve with NeRF. This is, for example, like this on the left is some sparse images of a hot dog on a plate. And when provided these inputs to a NeRF model, it provides you the entire 3D scene of the entire plate of hot dogs. So what we can do is we can now synthesize novel views from just some images which we get. So that is what NeRF does in an overview or in a nutshell. Now that we have the introductions out of the way, I'll just quickly tell you what we are going to cover in our talk, and then we can jump straight into it. So we have divided our talk into some levels, and we have tried to gamify it. And this is our character which takes you through the entire slide. As in this is you who goes through our entire slide. So the first is introduction to NeRF. What is NeRF? How NeRF came into existence. Then we talk about how the the essentials of NeRF, like generating rays. What is the NeRF MLP that we talk about? What is volume rendering? What is photometric loss? And then how do we enhance NeRF? So NeRF is good, but we also talk about or try to talk about a few little tips here and there to enhance how our NeRF performs. To begin with, let's formalize the objective of our talk a little further. Novel view synthesis refers to creating an unknown viewpoint, like something which we absolutely don't know, of an object provided some other viewpoint. So as we can see, the first view, this is something which we know, and this is a chair, which is the object of frame. Unlike my photo gallery, the object in frame was the staircase, and the previous hot dog, the hot dog was the object. So here, this is a chair, which is the object. The first view, second view, and the third view are some things which we already know. This is not something which we don't know, and this is these are the images that we get as our input. Now, what we want our NeRF model to do is predict the novel view or something which we don't know or something which we did not have in our data set, right? So NeRF tries to model the entire 3D geometry of this chair so that we get our unknown, kind of novel view which we synthesize. So as our character here asks us a question, why not capture the entire 3D scenery from the images itself? How does that help? Let's take a moment and try to observe the idea. We are now looking at a transformed problem statement altogether. From novel view synthesis, like synthesizing new views from a sparse set of 2D images, we have transited into 3D scene capture so that we have the entire 3D scene at our hand. This new problem statement will also serve as a solution to what we were aspiring to achieve. How difficult is it going to be to generate a new view if we already have the 3D scene at our hands? So transition from a novel view synthesis to entering into 3D geometry, we are tackling the same problem statement just in 2 viewpoints, right? We begin with a sparse set of images and their corresponding camera metadata. Next, we want to achieve a 3D representation of the entire scene as shown in this figure. So these are the images that we would have, and this is our bulldozer or the 3D object in frame that we want to achieve, but we only are given these images, image A and image B. The first part is to generate rays. So how do we generate rays? In this step, we march rays through each pixel of the image. So consider this pixel that I've kind of highlighted. From this pixel, if we shoot a ray, which is ray A, and from this pixel, if we shoot a ray B, these are the rays that we are trying to generate. And how do these help? We generate rays to get what do you call it? An objective on the 3D geometry. We want to project our 2D image into the 3D scene so that we can optimize our 3D scenery as we go along. Sample points is the second step. So in this step, we sample points, that is A1, A2, B1, B2 on these rays. We must note that these points are located on the rays, making them 3D points, not 2D points. So I'll just go along again. So first step is to have 2 images, that is image A, image B. Then we shoot rays through the entire 3D scene. And then we sample points. We try sampling points on the rays. And these rays are 3D, hence the points are 3D as well. Next, what happens is each point has a unique position, which is the XYZ or the coordinate system, as we all know, and a direction component, which is alpha, linked to it. So consider this point. This has X1, Y1, and Z1 as the 3D scene geometry, as well as alpha, which is the direction in which the ray has been shot. So think about how your camera orientation is to understand how the ray is going to get shot. So if your camera orientation is somewhat tilted to a 60-degree angle, the ray is going to have an alpha, which is 60 degrees. So if that makes sense. Now we move on to deep learning, which creates all the hustle and bustle. We provide these sample points or the coordinates and the alpha position of the sample points onto an MLP. And what we try to predict is the color and density of that sample point. So we know and we understand color. We do understand that the point here should have a color of a little bit of yellow. But what is density? Density corresponds to, is there an object on that sample point? So think about a point which does not have that object. So the density of that point is going to be 0. This makes sure that the ray or the volume rendering, which Ritvik will come later to, has something on that ray or not. Do I have an object on that ray? If I have an object, what is the color? That is something which we are trying to emulate now. Next comes volume rendering. So let's consider a single ray, that is ray A here, which passes through this pixel P, right? And we send all these samples along the ray A to the MLP. And this MLP gives you color and densities of every single sample point on this ray, right? What happens then? We get these colors and densities, and with the help of volume rendering, which again Ritvik will come later to, we kind of squish the entire 3D scene into the same color space or the same image that we have. So we have an image, we shoot a ray, we get all the samples, we send it to an MLP, the MLP produces or predicts our colors and densities, and we again get back the same pixel, or we would want to get a same pixel. We don't get the same pixel right at the beginning of the training, but as our objective kind of loosens up, as we tune the MLP, we get a similar kind of a pixel, and with the objective or the photometric loss or the loss for that matter, we try to emulate that image that we already have through the 3D sampling points, right? Now comes the photometric loss. So this is what I try to, kind of in a hand wavy gesture, make you all understand. So this is the original image. I shoot a ray, I sample the points, I get the MLP predicting a lot of stuff. And the prediction looks like this. After the volume rendering, I get the rendered image. And what happens now is that I do a MSE, or the mean squared error, or absolute error for that matter, of the original image and the rendered image. How does this help? It helps in making the MLP understand which part of the 3D scene is good or not good, right? We are trying to, what I'm trying to drive home is the point that our MLP is trying to memorize and understand the 3D geometry rather than the image. So right after the image, I get a 3D geometry, and the MLP is trying to overfit on that. Now we need to generate rays. So that was the overview of the entire NeRF architecture. Now I go on to a little depth of how we are going to, try out our NeRF model. And the first part that we know we have is an image, and from that image we need to generate rays. So this is the entire mathematical equation that you probably need to wrap your head around for generating rays. This is R of t, which is equals to O plus T of D. So R is a vector, as you all can notice. O is a vector and D is a vector. So what does this mean? R is the ray, which is a function of T. T stands for the sample points that we have. O is a vector, which stands for the origin of the ray point. So as we all know that if we want to shoot a ray, there needs to be some origin that we need to get hold of, or the reference point, and then we shoot a ray. So O is that origin point that we are talking about. And D is the direction. So if you all noticed that the alpha, I'll just go to that slide again. The alpha that we are talking about is a vector for us, because we need to understand how the ray, kind of propagates. So the direction is very important. So as we all know, RT is the ray, O is the origin, D is the direction, and T is the number of sample points that we have. So to build the ray equation, we need the origin and the direction. In the context of NeRF, we generate rays by taking the origin of the ray as the pixel position of the image plane. So as we knew that there were two images, image A and image B. So let's, for our very own benefit, think of this mesh as the image plane, right? And this is the camera, the blue dot is the camera, and the red dot is the origin, because that is where the image plane kind of intersects with the ray of the camera. So that is where the origin is, or the O vector is. And we shoot a ray through the origin vector with a direction, and that is how you see the ray forming. Now let's talk about sampling points. So first was to shoot a ray. Now we sample points, and then we go on to NeRF. There are two kinds of sampling points that we want to talk about. One is a uniform sampling strategy, and then comes a random sampling strategy. So as the name suggests, uniform sampling is where the T's, or the points at which we sample, are uniform. They have a similar distance and they are not random at all. So as you can see, T1, T2, and T3 are equidistant to each other, right? And then we come to random sampling. Random sampling is a little chaotic, but it also helps for our NeRF model, which we'll come to later, why this helps. But understand this, in this method, we add randomness into the process of sampling. The idea here is that the sample points come from random positions of the ray, like absolutely random positions of the ray. The model will be exposed to newer data. So think about that. Coming to uniform sampling, the model will always get T1, T2, and T3, which are equidistant. But when we talk about random sampling, T1, T2, T3 are random. Hence, we always are going to give the NeRF or our model new data every batch or every epoch, which is a great addition to our entire optimization scheme. And now let's talk about the NeRF MLP, which is the main heart and soul of this whole project. The NeRF MLP looks very simple, very clear. So it's actually, it does not have any convolutions. It is not talking about any attention, no transformers, nothing whatsoever. It's just basic multi-layer perceptron, right? And it's actually quite simple. Each sample point that we talked about has 5 dimensions to it. So what are these 5 dimensions? That is the x-axis, y-axis, z-axis, and the 2 directions, which are the polar coordinates, like the r and theta that we know of, which decides the direction of the ray, right? And the points. So the spatial location of the point is a 3D vector, that is the xyz, and the directions of the point in a 2D vector, that is theta phi, decide on the direction. Ben Mildenhall et al. Advocate expressing the viewing direction as a 3D Cartesian unit, which is something which is a little advanced, so I'll not talk about it now. What basically happens is we have this input ray, or the points that we were talking about. The point goes into a bunch of dense layers, and it also gets a residual connection, and again goes to a dense layer. Now, the important thing that I want to note, like drive home, is that the input ray does not have a direction as of yet. It just has the 3D coordinates, that is the x, y, z axis, right? And this gives you the volume density. So think about it, and I'm speaking out loud while thinking about it with my audience. You get hold of a ray point, and that ray point either hits with the bulldozer or does not hit with the bulldozer. It should not have any context to what this bulldozer color should be at this moment. A point just hits with a 3D object. Yes, no. That is what volume density tells us. It gives you a probability of whether or not this 3D point is, kind of intersecting with any scene or any 3D scene or geometry it has right now. So that is what we are dissecting here. And this again goes to the input direction. Like right after we predict the volume density, we are also taking the representation and concatenating it with the direction. And now with the direction, we get we produce RGB of that point. Why do we do that? Why do we segregate the two things? Like, why do we input rays and predict volume density while we concatenate the representation with input direction and predict color? So think about this. If you have a ray which goes from 60 degree, you will be able to see parts of your 3D scene wherever you are at in a different color. If you view it from a different angle, you will see a little change in the color due to reflection, due to a lot of other things which happens in our 3D world. So what these authors did, and which is highly, I'll say it's very quick and quirky to think, but it's very interesting. They kind of segregated the entire process in 2 ways. One is input rays, talk about the object. 2 is input directions and talk about the color, because the direction has different colors. So that is why when you saw the 3D hot dogs moving, I just go there quickly, and I'm sorry I had to do this a lot of times. So when you see this, can you see the shadows coming from the hot dog? So this is what I'm talking about. With every viewpoint, you will have different colors of the plate of the hot dog. So at one viewing point, you will see a shadow. At one viewing point, you will not. And this is very interesting to look at. So with that, I kind of covered the NeRF MLP, and now with volume rendering, and henceforth I'll hand it over to Ritvik. So I'll just stop sharing.
Thanks, Aritra.
Ritvik,
yeah. I hope my screen is visible and I am audible. So now we know that our NeRF MLP or our network is able to produce color and our volume density, right? But having these two separately is not enough. Our friend here needs to generate novel views, and for that he has to achieve volume rendering, which means that he has to use the color at that point and the volume density of that point, and as Aritra mentioned, squash it together and have a representation or a new view altogether from these two variables. So how do we do that? Now notice that volume rendering is not new. It has been like games and 3D visualizations have been using volume rendering for the last 20 or 40 years. So what the authors have done is take this from the existing literature and put that piece of the puzzle in their context. Now, to achieve volume rendering, you need this equation, and this equation might look like a lot and like it is a really tough challenge, but it is actually quite easy to understand. So just stick with me, and I'm sure we will understand it a little better when we are done. So this term right here, C of R, is the color of that point of the object. So if we go to this slide that Aritra explained, we are getting a rendered image right here, right? And that rendered image will have hopefully a new view, a novel view of this scene, and it will have colors. So what is an image comprised of? It is comprised of pixels having different colors, right? So essentially what we are trying to do is trying to create pixels for each, create or predict colors for each pixels of this rendered image, right? And if we go back to this equation, this term on the left is the color of that point or pixel of the object, right? And now let us go through the entire equation one by one. So R of t equals O plus TD is a ray that is fed into the network that Aritra explained a while ago, where the variable is the same as before. O as the origin of the ray point, D is the direction of the ray, and T is the set of uniform samples between the near and far points used for the integral. Now, near and far points is something that might be difficult to wrap one's head around, but think of it like this, that every camera or every viewing mechanism, even if it's our eye, has a near and far point or a limit within which it can view. So if we bring our hand very close to our eyes, we will not be able to make out or differentiate the objects. And if it goes like far off into the horizon, we will not be able to like make out the details. So that is basically the limits or the near and far viewing points for our eyes. Similarly, we will have something like this for a camera or for any recording system, and these things will be given to us. They will be inputs to the model. It is not something that we will predict or we will compute along the way, right? So with that done, sigma R of t is the volume density that Aritra mentioned. It can also be mentioned as the differential probability of the ray terminating at that point t. Now, what we mean by that is that so this ray, think of it like this. This is our existing view. This is our existing view, and a ray is being marched through it. Now, once the ray is marched through it, what does that mean? It means that a ray is originating at some point in the 3D view, and say suppose this is an object, and it is going like this, and every point we are taking a sample out, whether it is random sampling or uniform sampling, whatever. And what is happening is, if it hits that object, or if it hits that representation of that object as an existing view, it will terminate at that point, right? It will stop. That is what we mean by volume density or the differential probability. It is the probability of this ray originating at some point, stopping at that object, which is basically you can think of it as a way, you can think of it like that ray has found an object or found the representation of an object. So this is the differential probability. Sigma R of t is the differential probability or the volume density. Notice that C of R of t and sigma of R of t are two things that our NeRF MLP has already predicted for us, right? And there is this last term, which is T of t. Now, what is T of t? This represents the transmittance along the ray from near point Tn to the current point T. Think of this as a measure of how much the ray can penetrate the 3D space to a certain point. Now, Auditro mentioned something about shadows and occlusions, right? So imagine this again. A ray is originating from any point and it is going to hit an object. But not all objects are created the same, right? It can be something as simple as a shadow or a reflection. So it becomes important for us to quantify whether how much of the object or how much of the ray can be stopped by that particular slice of the object, right? So if you think of it like this, that your ray might hit that representation of an object, but there is no guarantee that it will stop. Why? Because it can be the shadow caused through another part of an object. Like, for example, we are trying to create a 3D view of a truck or a tractor, right? And it might have shadows and occlusions. So that point will be a measure of how much the ray can penetrate the 3D space. So there we have it. The color of an object in the 3D space is defined as the sum over or integral of transmittance, volume density, sigma r of t, the color at that current point, C of r of t, and the direction of the ray, d, sampled for all existing points between Tn and Tf, which is the near and far points of the viewing plane, respectively. So that actually breaks down this complex equation into a much more digestible form, right? And so it is also important to remember that this entire equation comes afterwards, right? This equation has no part to play in this MLP. Our deep learning journey or our journey of predicting color and volume density ends here. And then that color and volume density in an act of post-processing is plugged into this equation, which converts or squishes that volume density and color into the color of that pixel for a novel view, right? But there is also another important point that we are missing. And that last bit of thing is to define a loss which can be used to train the network. Now, the authors call this the photometric loss. Mathematically, it is expressed as such, where I is the real image, I hat is the synthesized image. Notice that this is nothing but a mean squared error. This function, when applied to the entire pipeline, is fully differentiable. This allows to train the model parameters theta, which is the minimization of this function, using backpropagation. And finally, our model is ready. We are good to train it to synthesize novel views. But our friend is worried about the size of the data. You see, this is not like other networks or other papers where we can use any data set to train the network. Here, the data must be different views of the same object. And to drive this point home, I will go back to this slide in the beginning, where this is all we have. Not exactly these 4 images, but we'll have, say, 100 or 200 or maybe even 1,000 views of the same object, which is not enough. Like, deep learning models are very data hungry, and you need quite a lot of data to train this model, right? And you will not be able to rely on a data set like ImageNet or something else to train this model, because you literally need the views of the same object from different positions. So what we must now do is artificially add more sample points so that the model can function well, right? And the first trick that our friend is going to use is called positional encoding. This projects the sample coordinates to a higher dimensions with a sinusoid pattern that actually helps in the overall performance of NeRF. And before we dive into positional encoding, let us look at a familiar encoding scene. So let's say we have 10 positions, index as 1, 0, 1, 2, 3 up till 9. The indices are in decimal system. If we encode the digits in the binary system, we will get something like this shown in the figure. The binary system is an easy encoding system. The only problem we face here that binary system is filled with zeros, which makes it a sparse representation. For deep learning or for like anything that has to do with backpropagation or calculus for that matter, we would want to make that system or representation continuous and compact, right? So the encoding function that NeRF uses is something like this. And again, if this equation looks a bit complex, don't worry, as this will make sense in just a minute. So to draw a parallel between the binary and the NeRF encoding system, let's look at this figure. And to further drive this point home, let's look at this. So this is all that the representation has to offer. We are taking indexes of 2 and then alternating between sine and cosine and plugging that into our encoding function. And we'll see a visualization of how that works in a second. So the sine and cosine function make the encoding continuous. And the 2 to the power I term makes it similar to the binary system. You can see a visualization of the positional encoding function, EX. The blue line depicts the cosine component, while the red line depicts the sine component. And I'll just let this play out for a moment so you get a sense of what's happening. Right. Now, with positional encoding, we have successfully transformed our coordinate system. We have projected it to a higher dimension, and that will help. But what we now need, and the second trick that our friend is going to use, is called hierarchical sampling. This is especially important as this will allow us to take a set of sample points and from it then train them, and from it extrapolate a second set of sample points and then train the model jointly using both of them. So let's see how our friend suggests we achieve that. First, we are going to build 2 identical NeRF MLP models called the coarse and fine network. And we are going to sample a set of NC points along the camera array using random sampling strategy. So as Auditra mentioned, random sampling will ensure that each time the sample point sees a new position, right? It is not going to be the same position as of uniform sampling. So you can see, you have already seen this figure, but this is how random sampling is going to look like. And we will call these points NC because they will go to the coarse network, or they will be used to query the coarse network. So the output of the coarse network, again, what is the output of an MLP network in NeRF? It gives us the color and volume density. The output of the coarse network is going to be used to produce a more informed sampling of points along each tree. And we'll get to that part in a moment. These samples are going to be biased towards the more relevant parts of the 3D scene. Think about what I'm saying in a saying. So we have existing views like this, and we are going to generate a novel view. So we are going to march ways through the object, and each time the object, the ray finds an object, we are going to sample, like we are going to produce the color from that point using volume rendering and our NeRF MLP. But once we produce the color, what happens is, if we use that color to then revert back to the set of sample points. So our input is a set of sample points, and through all of this marching of rays and going through MLP, we are getting a color at the end of it. That is our output. What if we reverse it? Get the input or the sample point from the output itself, right? From the color, we get the sample point. What will happen is that set of sample points will be more informed as to where we can find a 3D scene. It won't have a point that the array goes through that point and entirely misses the object. That won't happen because we are getting the input from the output itself. And so to do this, what we are going to do is rewrite our color equation over here to a weighted sum of all color samples. So it is going to have a weighted sum till the coarse points of the color representation and the weights of the MLP, right? And these weights, when normalized, produce a piecewise constant probability density function, which can be mathematically expressed as this. This is nothing but a normalization representation. And we can see the entire procedure of turning the weights into probability density function visualized in this figure. So we have coarse samples and we compute the weights from those density and we get the PDF representation or the probability density function. Now what we are going to do is from that probability density function, we sample a set of NF locations using inverse transform sampling, which is a mathematical sampling method. So what we are going to do is we have the color or the final weighted representation of the we have the coarse samples and we are going to convert that into weights, and then that weights will be used to compute the probability density function. This is what the entire procedure looks like. We have the coarse samples. From the coarse samples, we achieve the probability density function. And from that, we sample the fine points, which is called NF. Now we have both coarse and fine points for the NeRF MLP. Now that we have both NC and NF set of sample points, we send these points to the fine network to produce the final rendered color of the day. This ensures that the fine model actually has an extra set of points for predicting color and volume density. And there we have it. All of the levels have been successfully completed for understanding neural radiance fields. And what we tried through this presentation was to give you a sense of what are the basic components or what are the prerequisites and various things that we need to cross or understand to build a neural radiance field. Because in its essence, the NeRF model is starkly different than any other MLP or deep learning project. We do not have a simple architecture like an image data set and then we predict a class or something else from it. We are essentially generating something novel from something that we already have. So we looked at the initial problem statement of NeRF and then understood about generating rays that we need to achieve the final results. The NeRF MLP, which is the only deep learning part in it. We also understood the math behind volume rendering, which is something that we use after the MLP has given us predictions. We understood the loss function that drives this entire machine. And finally, we looked at some methods that the author proposed to enhance NeRF. However, in the interest of time, we could not give a complete code walkthrough of this entire process. But we do have some bonus links for you. If you want to look at a minimal code implementation or an in-depth tutorial on neural radiance fields, check out our Keras implementation or the blog post series from PyImageSearch. Both of these are written by us. And finally, we would also like to thank some people before we end this talk. Ben and his entire team who came up with this beautiful idea of NeRF. We think it is a seminal paper on all fronts. François Cholet, who guided us greatly on the Keras implementation. Joko from Hugging Face Reading Group, who had this idea of 8-bit games for slides that we borrowed here. And the entire PyImageSearch team for always supporting us in every aspect. And finally, if we have some questions or discussions from the community.
Hey, so thanks for sharing this. That's the first thing. And there are a couple of things that I wanted to ask regarding the first one is, again, like, I think you mentioned about like the number of minimum images like required. in views like hundreds and thousands. But is there any specific requirements? Like I see like angles and angle at which the image is taken is definitely an input. So is there like any requirement for these images to be a part of NeRF a data set, like as the minimum metadata that is required for training this image training images, like to produce a 3D rendering?
Cool.
Ritu, are you going to take it?
Yeah, I can take it.
Cool.
So I'll go back to this slide, and wow, we have a lot of slides. Yeah. So in this slide, you can see that the images are first of all, thanks for the question. Yes, we need some prerequisites for the images to be. They have to be for the first variant of NeRF or this paper, neural radiance fields. They have to be a certain representation. These have been artificially generated images. These are not real images. They have to be something called a call map representation, which is a representation scheme where you represent the XYZ coordinates in a certain manner so that your images so to expand on this, think of this as something like this. When you click an image, or the metadata that you need for you to understand or build the visual scene is something that is not inherently there in the scene, in the image itself. It is something to be deduced from, something we need to deduce, right? And what the call map representation does, or what some other contemporary representation does, is it builds a system where we can deduce the XYZ coordinates or deduce the camera viewing angle or the camera calibration that is needed to transform these images into novel view. And that is something that for that the NeRF that comes before or pre-processing into NeRF, right? When the NeRF, when the images go into the NeRF MLP, it looks like this. But if these images have to be processed, or if these images have to be generated, they have to be generated a certain way using a certain representation. Of course, that is a crutch, and that is something that should not be present in a deep learning system with all these advances. So there are variants of NeRFs that come up with ways to mitigate that. One of these papers is called NeRFis. We also have GNeRF called GAN-NeRF, which mitigates its problems. But for the first paper, it was essential that the representation of images, or the metadata, as you mentioned it has to be in a certain way, so that the world to camera and camera to image mapping is easily understandable or easily deducible from the images. Does that make sense?
Yeah, it makes sense. And I assume like transmittance is also another parameter, like or a variable that has to be present in the training
Yes.
data. Okay. I don't know if anyone else. I have like a couple more questions. I can go through them, but if anyone else like wants to ask any question, like feel free, I guess.
Yeah. So okay, my mic is causing a little problem. Also, can you take this one?
Yeah. I'll take that.
So the next question that I have is like, what if the two views are from two different distances? Like, for example, the first one, like here, like we actually see like all of them are from the same distance, right? So what if you have like the first view, say at 2 feet distance from the actual object, and the second view that you have is probably like 20 feet away? So how would yeah.
So that's a brilliant question. So this question was itself, kind of a question that the authors even elaborated on. So what they suggest is you should have a kind of a setting where you have a spherical dome, where the object sits right in the center, and on the spherical dome, which has equidistant, all of that stuff, equidistant viewpoints, we have viewpoints from that. Now, what happens if you don't have a static spherical dome? You have that was your question. You have a dome wherein one point is from 2 meters, other point is from 20 meters, and all that stuff. What you need to understand is with NeRFs, we are just going to give some sample points to an MLP. So with that, you also have to understand, like you have to inject the information that this is from 20 meters. So do a volume rendering in that sort. It's from 2 meters, do this. It's from 1 meter, do that. And like I have noticed this because I am not very good in Blender or the one like as the authors are, because these hot dogs and all the chair and stuff are produced from Blender. So what I've seen that if there are different viewpoints on from different views, and we use just the simple NeRF MLP without injecting anything, it has a very distorted kind of a 3D scene because it does not understand where the sample point is coming from. So that is a problem that we would eventually have to mitigate with different other possibilities. So recently, as I'm not very sure, recently I have gone through a paper called iNeRF, which tries to mitigate this by doing something called, like, they have these two models where one model tries to capture all of the distances, because that is something which it does, just the distances. It kind of predicts from where does the sample point come in, and the other model which kind of does a contrastive loss tries to figure out what this sample point should be. So trying to mitigate where from the like what is the distance, as well as how do we render the loss. So that kind of a setup. But this was a really good question. Thanks for that.
I think am I audible now?
Mm-hmm.
I think BlockNeRF also does that. So there was a written recent hype about BlockNeRF, which also does that. And it becomes essentially important because you are eventually going to view a 3D point from anywhere, and so
anywhere from it.
Yeah, it becomes important for you to not just understand XYZ, but how far off is it from the object that you're trying to render. And that is also
a good point.
That is also important because you are not, as Arthur mentioned in talking about occlusions and reflections, and this is something that we see come up over and over in 3D geometry or 3D rendering, is called ray tracing. So you are not just trying to predict color or the volume density of a point, you're also trying to predict how the light affects that point. So your viewing distance will greatly affect that as well.
Okay, thank
Thanks
you.
For the question.
Yeah, no problem. I only have like one other question. This is something related to that I didn't probably understand well. I guess like the positional encoding, like where do you like what do you encode? Like which part of this the whole thing, like do you actually encode is the question.
Sure.
So I didn't understand that part of it, but yeah.
So you remember this XYZ and the viewing angle, right? So this is our coordinate and also their direction. So this is something that is going into the network, right? And if you embed this into a higher into a sinusoid pattern, and then in a higher position, what is going to happen is that it will automatically make the network more robust. And there is actually a paper by the same authors from NeRF called Fourier feature representation. I'm not sure about the name, but it is referenced in NeRF, where they talk about why does sinusoidal encoding help us in achieving this. And to answer your question, what we are essentially doing is XYZ and the viewing direction are our coordinates or our inputs to the model. And these inputs to the model are projected in a sinusoidal pattern on a higher dimension. And that will help the model learn faster in a more robust manner. Robust, when I say robust, I mean that not robust to adversarial attacks, robust to performance.
Mm-hmm. So in this case, like the ray is not a straight line; it's instead a sinusoidal and a cosine waves, like with the sample being.
That's an interesting way to look at that, but I'm not sure I can say that it's incorrect. But think of it like this: you have a ray. I'm sure you can like see me. So you have a ray. You're taking the points from it. That points are now transformed in a space which is sinusoidal, right? So the plane of that space is sinusoidal. right?
Okay.
So the points embedded on it are sinusoidal automatically.
So you're projecting the less number of points to a more number of points, so that like you have
exactly
a more
your
points
dimensions
for,
are increasing.
Okay.
Yeah.
Okay. That's good. Okay. Thank you.
Yeah. So if anyone else has any questions, discussion, something that they would like to ask.
Just going to say that Reddy, is it? Yeah, I love those questions, and it kind of gives me an excitement that we were on the right track to get so many questions, which are like top-notch questions. So thank you for that.
No problem. Thank you so much for putting up this.
So if anyone's wondering about the slides, or if they need it, we will be making it available through Jian. We will be emailing her the slides, and maybe she can put it up in the community. And like, other than that, I hope that this session was useful to everyone watching. I hope we could give some sense of what NeRFs are and why is it a seminal paper and a seminal direction. Why so many conferences mention NeRF, and why there are so many variants of NeRF coming out every conference. Again, if you need the code implementation, we have them on Keras and an in-depth blog post from PyImageSearch as well. And yeah, so like, if anyone has any questions, please.
Yeah, this was really great. This is my first exposure to this sort of 3D stuff. But I think like you went through over the mathematical explanation and you have the code. So I think it's a really good tutorial for people to go through and learn about this. So I really appreciate this.
Thank you.
I think it's really helpful. Thank you so much for this.
Yeah, thanks for organizing as well, and thanks for the talk.
Thank you so much.
Thank you, everyone. Bye.
Thank you. Bye-bye.